And then I am happy to introduce Shun Yu from RISE. Please let us know more about who you are. And this webinar is presented thanks to a project called Lignin for Future. And it's in collaboration with Sting Bioeconomy, Paper Province, Kristinehamn Municipality, and RISE is the main partner, and it's financed by the region Värmland and the EU structural funds. So Shun Yu, I hope you are with us.
Yes,
Yes.
Can you hear me?
I can hear you perfectly well.
Okay.
And see you also. Great.
I will start share my presentation then.
Yes, please do so. And also, if you wonder who else has this lovely background, it is Ulrika from RISE who is helping out with this webinar. And now we see your presentation, Shun Yu, perfectly well.
Yeah, so, thank you, Maria, for giving me this opportunity to present actually my background and my research field. I have to be honest, I'm quite new to the lignin research field, but I start to collaborate with researcher who works with lignin material, and I try to use my technique to help them to address some of their questions. So from the title, you can read synchrotron radiation-based X-ray technique. That's basically my research field or my research tool. I'm a X-ray characterization specialist working at RISE. So actually, there's a reason why we RISE recruit X-ray specialists. In the southern city located in Sweden, Lund, we're actually building two world-leading facilities. One is called MAX 4, which is this round building here. It's a synchrotron radiation-based X-ray facility. There's someone with me with a really heavy breath.
No, we have someone with the microphone on, so please keep it.
Yeah, and another facility is called ESS, which is here. It's called European Spallation Source. These are the best of its own kind to the present. And it happened to be in Sweden. So RISE, as the largest research institute in Sweden, we decided to step in to help our own researcher and the industry collaborator. So we formed a team. Actually, it's not just me. And here's the list of the team member. We're coordinated by the team leader, Nicholas Loren. And most of the team members are situated in RISE Lund here, if you see my mouse. Our mission is actually to collaborate with a facility we call MAX 4 ESS, a large scientific research facility with academia and the Swedish research, Swedish industry to help them to use the technique at the facility and in their R&D research. So each of the members in the team covers a different type of X-ray technique. And I have my background in X-ray spectroscopy and X-ray scattering, so you will know more about that. So why X-ray? Well, jump back to the previous slides. MAX 4 is an X-ray source. ESS is a neutron source. While we build two different large facilities at the same location, actually they complement to each other. Both X-ray and neutron, they interact with material, but they interact at different part with material. X-ray only sees the electrons, mainly sees the electrons, and the neutron sees the nuclei. And we know if we put the nucleus and electron together, it's an atom. So here's a vivid example actually from the Paul Scherrer Institute. By taking the same radiography of a camera, you see X-ray and the neutron, they see different part of the same camera. That's because the X-ray will be absorbed more by the heavy element, and the neutron have rather peculiar behavior, absorption behavior, mainly absorbed more by the organic stuff and some isotope of the heavy metal. So if we have a material, we have our interested or the material question we care about. It can be the morphology inside a bulk material, it can be an atomic scale arrangement, whether it's amorphous or crystalline, or it's an electronic structure in graphene or other material, or the chemical structure of the material if a metal is oxidized to 2+ or 3+ or 6+, then we come to this facility and we can find the answer for all different levels of material question. But actually, we need a closer look into the X-ray spectrum. X-ray is not just X-ray, it's actually have a finer defined region, extreme UV light, soft X-ray, and hard X-ray, and different. In principle, they're just electromagnetic wave, but they interact differently with the material. And for most of X-ray, it happens to correspond to the electron transfer between different orbitals. So which makes the X-ray a very powerful tool to determine the electronic structure inside the material. And this is also the traditional way how we generate X-ray, which is by bombarding a specific element with a high energy electron. Then the X-ray will generate either by the impinging electron changing the direction, is called Brown-Stallone radiation, or a more specific due to the excited orbital transition from the higher orbit 4F or even 5, jumping back to the 1S orbital, then it will release a specific with a very well-defined wavelength of X-ray. And I will come back into details how to, when and how we can use soft X-ray and hard X-ray later on. But let's come to the general picture about X-ray. When you first talk about X-ray, I believe everyone just, this image will pop up. So this is the first X-ray image of Rankin's wife's hand, I believe. So as you can see, the X-ray will go through the flesh, and we see a clear shadow from the bones and the rings. So what does it mean? It's actually X-ray depends on which energy we have. The X-ray will interact with material differently. And we say the lighter material, like the flesh, meat, will be more transparent to the X-ray. And the stronger X-ray, harder X-ray means with a higher energy, the deeper material it will go through. So this is already to give us at least 2 hints. So if we can tune the X-ray through a different range, then we can selectively probe the information we want, right? And then if we want a bulk information, we need a harder X-ray and a stronger X-ray with a lot of flux. So where do we find those sources? We come to a synchrotron source. Compared to the traditional way to generate X-ray by bombarding a specific material with the electron, and here the synchrotron will generate the X-ray in a different way. Instead of bombarding the electron onto a target, we let the electron travel at close to the speed of light in a big circle and force them to turn the direction. And while they're changing their direction, due to the relativistic theory and some Doppler effect, it will release a strong light pulse along the tangential direction. And then we can conduct the released light pulse along the tangential direction to a so-called beamline. And after a sequence of optics for the X-ray region, then we can select a certain wavelength of the X-ray and do the experiment. And So the advantage, why we need a synchrotron. So as you can see, this is to the left, this is a typical molybdenum target generate X-ray. You have the specific specific wavelengths with relatively high intensity, but of course, the higher the better. Is the best cases, they are high everywhere. Then this is a similar diagram from a synchrotron facility. As you can see, at the synchrotron, we have much higher flux if you compare to the powers 10 to the power 7. This is brilliance, I believe. This orders magnitude higher. And the energy is more or less continuous, tunable without very sharp peak. And the emittance is low. There's certain benefit of that, which gives a high coherence. Okay, this is the brand, market brand for the synchrotron, like high coherence, which means we can get more detailed information of the material, low emittance, which means we can focus beam to a very small area down to several tens nanometer, and then we can study the structure in a small region, like several tens nanometer. And flux is orders magnitude high, which means we can follow some material change in the real time. So X-ray technique depends on how they interact with material. There's a different technique, but we can always group them to 3 different categories: scattering technique, imaging technique, and spectroscopy technique. Since X-ray is in principle an electromagnetic wave, it will interact with material through the refractive index. And it's a complex number, but it contains 2 parts, because the real part is dispersive, the imaginary part is absorptive. So what does it tell us? So if we use scattering technique, we will get where the atom or material are, and how do they look? Are they big or small? And if we turn into the spectroscopy technique, we will be able to tell who they are, if they're iron, cobalt, nickel, and how do they react if it's an iron 0, well, 2+, 3+, or even for carbon or oxygen, we can also study that. So a little bit more on the soft and hard X-ray. Soft X-ray basically interact with the environment much more stronger compared to the hard X-ray. So not all the X-ray will go through your hand just like that. Not, at least not for the soft X-ray. So actually, for using soft X-ray, we need a vacuum surround our sample. And for hard X-ray, it's like the CT in the hospital. You don't need never put the patient in the vacuum chamber. And so soft X-ray interacts with material strongly, which means only a very thin sample can be studied. And for the hard X-ray, you can put a bulk material. And soft X-ray have a better electronic and chemical sensitivity. And for hard X-ray, it's more probing the atomic arrangement and material morphological structures, since it can go through. So let's come back to the scattering and diffraction region, which happen to be the technique I sit on. In the modern approach, it's fairly simple. We have the X-ray come from the synchrotron, we put the sample there. Then modern detection technique has a 2D area detector. So as you can see, if we put the detector fairly close, the scattering angle is large, and if we put the detector far, the scattering angle is small. Then this basically gives a name of different technique. If we put it far, it's called small angle X-ray scattering, SOX, and what it probe is a nanoscale structure. These all 3 are just a paper made of nanocellulose. Well, it looks similar, but actually their scattering profile looks completely different because they have different porosity. And again, taking an example of cellulose have crystalline structure and it diffracts a lot. This is standard XRD. And in the scattering field, we call it wide angle X-ray scattering. It's nothing different compared to the XRD technique. And if we put it even closer or even with higher photon energy, by doing a mathematical trick involving the Fourier transform, we can get a pair distribution function analysis. This is a powerful technique. So one can reach the bond-to-bond length inside your material, and regardless if the material is amorphous or crystalline. Then all this is governed by the Bragg's law. So as you can see, just by traverse a detector far and close, we can cover a very broad range or very broad length scale inside the material. And a little bit on how we analyze the material diffraction pattern. So this is a standard diffraction pattern. It looks symmetric, but we can unwrap it into a polar coordination with the center sitting here and the radius going out, and the angle goes minus 180 to positive 180. So by doing that, we have two approaches to study. If we just follow the radius, the intensity change as a function of the radius, we enter the standard regime of XRD or SAX. Then we can study the material phase, residue stress, grain size, morphological. And if we plot the intensity as a function of the azimuthal angle, then we can get orientation information. So an example for the carbon fiber, which I happen to work with by using the lignin sources. So by using scattering, you can study how the fiber is oriented, the crystalline structure inside the material, the pore size, and also the orientation. And here's another example, like in the carbon material divided by different resources, then we will see multi-scale structure from the large particle micropores and atomic level structure. And together with my colleague Andreas Benson, so we also study the lignin-derived carbon fiber by using the same model, so we can really extract a different structure at a different level. And of course, people would like to use more complex model, and actually my colleague and I, we also explore the possible solution by using machine learning algorithm to help us interpret that. Then we generate a different, use computer to generate a different structure. And this structure can be simulated into a scattering curve by using Fourier transformation. Then we classify that. So we have tests on different random Gaussian field, fiber, sphere, or holes structure. It worked quite well, actually. As I pointed out, hard X-ray can go through the air. So which means here is where you put the sample. Then surrounding is just empty. So you can put whatever test environment you have, including liquid phase, mechanical test, vacuum, of course. Hard X-ray do not require a vacuum, but if you have a vacuum condition, you can put it there, and battery electrochemical cell. And people have previously, for polymer material, for example, you can put melt spin processing into the beam. Then you can study at different position after the die. Then how does the material structure change? You can put a microfluidic channel and look at how the material assemble. In this case, it's a cellulose fiber. I believe if you can flow lignin through some channel, you can also do that. So just to summarize what we can do with X-ray scattering and then hard in the synchrotron, if you have a lot of samples, that's not a problem, because as a synchrotron, by using synchrotron beam, one sample just need a second, not more exposure time. More than that, you would damage your sample. And which means you can screen hundreds or thousands of samples, especially some facility have the robot to help you. And this is just a case for the diffraction case. And for small angle X-ray scattering, several tens per day is achievable. Another thing, with a high flux, one can study a dynamic and the kinetics change, which means follow the reaction or follow the heat treatment. And here we probably can time resolved. This is a lignin carbonized at a different temperature, and we compare the result by different, which shows, yeah, indeed the temperature have an impact on different source of the lignin. And at a synchrotron, the emittance allows us to focus the beam to very small area. In this case, it's a metal sample, actually. We use a small metal beam around 1 micron to register a bigger area. Then we can fit the XRD peak into the different diffraction pattern and to extract the different phase. And we migrate this technique actually to a lignin cellulose precursor. And we found out there's a core shell structure distributed evenly. So the lignin actually the content of lignin have an impact of the core shell structure. And this is just a 2D projection scan. Actually, if we rotate the fiber, in this case, like what they have done here, and then we can introduce a tomography technique. And in this case, as you can see, we do X-ray diffraction tomography, and this is a phase, the crystalline phase distribution inside one carbon fiber cross section. You see they're not evenly distributed in this case. Let's see, I use much of the time. I will speed up. Then let's jump back to the soft X-ray. It's a really busy diagram, but what I want to see here is for the soft X-ray, they're very sensitive to the different element. So it's element specific. Different energy level has a well-defined position. So which makes us easily probe the chemical and the electronic structure. And what's popular as a synchrotron is we don't need a vacuum. Yes, now I correct myself. Standard XPS, you need a vacuum because we use soft X-ray, but we, as a synchrotron, more and more end station introduce ambient pressure XPS. Then in this case, based on advanced vacuum technique, we don't need a vacuum around our sample. Overall, the beamline is still under a good vacuum, but if you're interested in, like in this case, what we study is a cellulose surrounded by a water layer. The water not only gives a real resembled case like how cellulose and water interact, but they also help us to screen the charging of the sample. And another case is a hard X-ray XPS. If you would like to probe your material a little bit harder than the standard X-ray, you can use a Hawk space as a synchrotron. And then instead of probing things less than 10 nanometers, then we go from 10 to 100 nanometers. That's also possible to study the deeper electronic structure inside the material. And these two techniques have been very powerful for catalysis, electrochemistry, chemical reaction, and in situ interaction with liquid. And at synchrotron, we have another technique, which actually very popular among our team. It's called PIM. So just doing XPS sometimes may be boring because you just look at the curve. What if we can convert the curve into an image? This is what the technique gives us, called photoemission electron microscopy, which basically each point can be a curve, XPS curve. And it has been very popular for graphene related research. And here actually we team up with Bright Day Graphene, and we went to the Max PIM beamline at Max 4 laboratory and studied some of their carbon material derived from lignin. So it's a still ongoing project. Unfortunately, I cannot share you the results yet. There's another technique. It's similar to the PIM, but actually, if we cut the sample very thin means down to 100 nanometer for carbon material, then basically even the soft X-ray will go through this specimen. And then we can work on the X-ray absorption technique around the carbon edge, which gives an advantage to tell the difference. For example, where is the cellulose, where is the lignin? And this is a standard X-ray absorption for cellulose. This is lignin. Clearly, at this position, there's a great contrast between the cellulose and lignin. And we can use this to distinguish the spatial distribution of them and even the chemical structure of them. So, and at the end, I would like to point it out, at the synchrotron, we can do tomography. This is not my field, but I found this very interesting because the high flux, one can follow thing change in 3D. This is like a foaming reaction inside some liquid solution, and you can see how the bubble develops or some foam develops. And in a three-dimensional image, I think that will open other door for your research for a lignin-related formulation. And with this, I would like to end my presentation. Sorry, I used much more time, but I hope it gives you some hint how to use this technique. Yeah.
Thank you, Shun, for your presentation. Very illustrative pictures.
Yeah.
And if anyone has a question to type down, you do it in the chat. You find it at the bottom of your screen. If you want to stop sharing, Shun, then you can see the chat as well if the questions pops in. And we see you in full screen. And I'm curious, what would you see as the next step if you are in charge and unlimited of everything? What would you like to happen as per next?
For the lignin research, or
related to your presentation, what would you love to happen?
My personal interest in the in situ or in operando study. So I would like to use a hard X-ray to follow the material change during the real time, the heat it up or cooling it down, or give a shock impact, or other things. So we have done different tests, like coupled with a humidity controlled tensile test for the material to test a different polymer composite or paperboard. That's my interest. And also my personal interest lies in the water purification and environmental remediation. That's why I focus more on lignin derived carbon in this case. And I believe both soft X-ray can look at the chemical structure of carbon. So carbon chemistry can be very complex. Also we use hard X-ray to follow how the water is purified. For example, we can dope some heavy metal elements, see how their chemical structure changes during the purification process. Then we understand if the chemical design works or not. So this is my personal interest, but it may not cover everyone's interest, but drop me an email if you have any question on how to use this technique.
We have one question here before we let Anna in. Nice presentation and interesting results. First of all, I'm curious about the carbonization of lignin. Can you explain a bit more about the work you mentioned about impact of temperature on carbonization of different lignins?
Okay.
In short.
Yeah, in short. So, well, that's actually it's a collaboration work together with Omid at Rice. And so what I can see briefly summarize, when we use higher temperature, we actually opens up more pores, and I see for soft woodcraft lignin, it's rather consistent, but for the hardwood, it's more changes happen. The several hierarchical structure develops. So.
Thank you. And we can also mention a teaser for the next webinar, which will be the 16th of March, where Andreas Bengtsson from RISE will talk. And what he is doing a lot of is spinning carbon fiber out of lignin. Okay, we have one more. We're quick, and then we'll let Anna in. I see you, Anna. Indeed, a very informative presentation. I just have one question. Suppose you're using lignin as an additive with any other polymer. Is it possible to see the blend mixture in VAX or PDF?
Well, as VAX and PDF doesn't tell you the chemical structure. It's just tell you the material structure. If you it's difficult to say like how well it's dispersed, and it's up to which degree, like which scale. If the inhomogeneity happens at millimeter scale, of course, I use a micron beam, then put a different position, I will see a difference. But if the inhomogeneous happen everywhere in nanometer scale, then we need to think about that. So it's cannot be summarized as one sentence, I'm afraid. So
good. Thank you, Shun, and thank you so much for presenting. And I hope you stay and listen to Anna. We say hi to you from Bright Day Graphene. Hi, good to see you.
Yeah, thank you. Good to be here. I will share my.
Yeah, and you remember the trick for the sound as well, because
yes,
we are very excited to hear as well what you will present.
Come on, there.
No worries, and we can see it perfectly well. Very good.
So, yes.
Yeah, please, Anna, introduce yourself. Who are you to those who don't know? And then we are curious to listen to your presentation. Please.
Yeah, thank you. Thank you for inviting me to this webinar. My name is Anna Carlsson, and I am the CTO and one of the co-founders of Bright Day Graphene. And I'm also really happy to present at the same time as Shun Yu, because as he mentioned, we have a really interesting project together, which is ongoing. So Bright Day Graphene was founded in 2017 by me and Malin Alpsten. And we offer green graphene for high-tech applications. And we make our graphene from lignin as a raw material. So this makes our material then has, of course, a renewable, comes from a renewable resource. And my background is within fuel cells. So I did my PhD within fuel cells at the Research Institute in Germany, and then I continued to work in that field for a total of 10 years. And during this time, I was getting more and more annoyed with that the materials used were not so super environmentally friendly. And I also saw the same trend within the battery field. And that made me start to think about how can one do this in a different way. And that was sort of the seed for Bright Day Graphene. Malin and I started this company based on an idea that it should be possible to make environmentally friendly energy storage materials. And then that was the primary thought. And then making graphene from lignin came out of that. So the same year as we started, an article was published, and this was actually also published in Ny Teknik, about all the different ways you can use graphene and carbon nanomaterial as a potential substitute for scarce metals. This is a list where we have tried a little bit to replace indium actually with transparent electrodes, but I cannot say that we have come far in implementing this list, but it is like inspiration for us to see how much we could replace in the future, and to really replace material which has to be mined to a renewable carbon material that does not even have to be recycled. And I think this could go a long way in reducing the toxicity of the environment. So this is a basic overline of our business model. We take lignin as a raw material. We make graphene out of it in our future factory. And we made actually a little film to explain the flow of things that I want to show you. So this is a picture of the material that we make. And our graphene material has comparatively a large size. And this is very good for conductivity. And they are both electrical, they conduct electricity and heat. And they have a large surface area and low weight. And it's green from the perspective that it's a renewable source and we don't use any toxic chemicals in the production. And if one would use, so graphene is very often used as an additive to other things. And one example of that is if one would use it as an conductive additive in a battery that could generate a longer lifetime and faster charging. And of course, there is so many application areas. And as we have been working for a while, we have been looking at many of different application areas, even non-energy storage areas, and we are still. But if we look at the projected graphene market, the blue one is for 2027, it is projected that the absolutely biggest use of graphene will be in the energy storage market. And composites and sensors are also quite big, but definitely the biggest one is energy storage. And there are so many ways in which one can use graphene in energy storage. One can make electrodes for supercapacitors and make those supercapacitors perform closer to a battery, but still much faster. One can use them in fuel cells to build like a catalyst support, as we don't know yet how to replace platinum with it. So we have to support the platinum, so the platinum stays small and have a big surface area. And as I mentioned, for batteries, it could be used as a conductive additive. And this is actually where we're planning to start, because the battery market is growing so much, and it's because of the electrification of the automotive industry, of course. And there is a huge demand of batteries in the near future. And we know, of course, of Northvolt here in Sweden, but this is only one out of 33 gigafactories which are being built in Europe, only in Europe right now. And 7 of them were supposed to be up and running in the end of 2022. I'm not sure if that actually happened or not. So what does this imply for us? These companies, because of their demand, they can only engage with material producers that can produce a lot, and they require samples to up to 5 kilos from us before they start to consider us as a supplier. So scaling is really of the essence. But in the meanwhile, we have started to test with smaller battery producers and are getting interesting results. And what we see is that we need less than 1% in the cathode, and from this one can see an improved lifetime and faster charging rates so far. So this is a comparatively easy way to apply graphene, which gives a huge impact. And it's a really good place to start, we think. So far, we have been working with a lot of different companies. We have done customer projects with Alfa Laval, Optipac, P-Foul, and Klabin, and we are just about to start one with IKEA. And Altris and Ligna Energy are companies which we are looking to start to work with, and which we have been starting a little bit to work with. And we are as a small company, we have to collaborate a lot with others, and of course, RISE and Lignocity is a great collaborator for us, as well as the Sting Bioeconomy, which were earlier mentioned, is our incubator, which we are still involved with because they own a little bit of our company. And we have gotten fundings from Vinnova, EU, Almi, and Energimyndigheten. I think their logo is not here yet. And another way to be, we have participated in some startup competitions and also won a few prizes that we are very proud of. And this is our projected timeline. So we want to build a 1 ton a year industrial pilot. And this is starting next year. This is mainly due to the financing and also the delivery of all equipment that we cannot start already this year. And then we want to scale up to 1 ton and then, no, sorry, 100 tons and then 300 tons. And yeah, that was all that I had, a shorter presentation, but yeah, you are always welcome to contact me and Malin if you have any questions. You can take down our email addresses here, and yeah, if you have any questions, I could answer them now.
Thank you, Anna. Always interesting to listen to you, and we hope for the best for the future. And the questions are coming in. At what scale graphene from lignin can be produced?
So we are currently a little bit below gram scale in our lab. But we have blueprints for our ton production. And this is our first target, but of course, at the moment we are a bit limited, and our final target is of course 3,000 ton or more.
Great. What is the biggest difference of using softwood versus hardwood lignin in your process?
So we have mostly worked with softwood because this is what we had most available. But in one project, we also worked with hardwood, and it did actually work better than I thought, because the hardwood lignin is it's more chaotic than the softwood lignin. So I wasn't sure that it would have the required time to rearrange itself, so to say. But when it came to thinness, it became very good. But there are some holes in it, actually. But it still becomes a nice material, I would say.
Good to know. And a question about investment. How large investment is required for 1 ton and 100 ton respectively?
For 1 ton, it's 30 million crowns and 150 million crowns for the 100.
Very well. And do you have secondary or sub-products on your process?
Secondary or
sub-products, like if something else comes out of your process, but the graphene.
Yeah, we said before that we get like we get parts like amorphous carbon as a side product, but we have been working to minimize that. So now actually all of it comes out as graphene or graphene oxide. So that's a great improvement which happened the last half year, which improved the yield significantly.
Very good. More coming in. If you stop sharing, Anna, you can also see them already in the chat if you like.
Yes.
And then we see you on full screen. And the next one is first praising your very nice presentation. Can you comment on the ability to graphitize lignin? What is the difference between hard carbons from lignin and graphene in terms of processing conditions? A big question, right?
Yes. So I think that it's not, I haven't not really made hard carbon myself, or maybe some in a accidental manner. But I don't know which is the proper way to make hard carbons. I would say that we are using a template to form the graphene, which is also a catalyst. So yeah. And we have a quite reducing environment.
Yeah, we have Omid in this meeting. I don't know. Do you think he could add a comment to this?
Yeah, if he wants to.
Yeah, we see if he wants to. Omid, if you like, and if you are next to the computer, if you can unmute and make a comment to this on the hard carbons.
Sorry, maybe I missed the question. What was the question?
Yeah, the large question was if Anna could comment on the ability to graphitize lignin, and what's the difference between hard carbons from lignin and graphene in terms of processing conditions. Do you have a short answer to that?
I mean, hard carbon is non-graphitized carbon. So basically, if you carbonize lignin in the normal condition, it will form hard carbon. So for the graphene or for graphitization, basically, so you need to form this order, the structure. So you need some sort of like a very high temperature of catalyst for that.
Very good. Thank you, Mid, for helping us out.
No problem.
Thank you. And back to financing, following question to the one before. Have you secured the capital for the pilot with the 30 million Swedish crowns?
Not completely.
So,
no.
Investors are invited, yeah?
Investors are very much invited.
Very good. And it keeps coming in here. Do you have a facility to conduct a test for lignin, or do you have a specific partner or institution for a test?
Actually, we collaborate with Omid. So he is our lignin, situ lignin expert.
Yeah. Good, Anna. And thank yous are coming in. Very good, Anna. It's only a few minutes left till 3 o'clock. So I say a thank you to you. If people have more questions, they can stay. And then after we stop the recording, we will be less formal and speak out our comments. but that will not be recorded, as we said. And again, next webinar is the 16th of March. So there will be, of course, a link sent out where to register. And Andreas Bengtsson from RISE will be talking about carbonized lignin and the spinning of it. And Åsa Östlund from Tree to Textile is the second speaker. But there will be more details coming later. So thank you so much to Shun and to Anna for taking the time to present today.
Thank you.
Very good.
Thank you.
And thank you to Ulrika being in the background, and to everyone taking their time to listen in and typing questions. That makes it all. So lots of thank yous keep coming in now in the chat, and that's all to you, Shun and Anna. So thank you very much.